Hello everyone, my name is Kirill Semenov. I am a PhD student at the University of Zurich, and today I will be presenting the project that we did together with Professor Martin Popel from Charles University, which is called InCa and InDia and is dedicated to new approaches in inline casing and diacritization preprocessing. So we should begin with the clear, strong side of the subword tokenizers. They can successfully avoid the out-of-vocabulary problem and successfully split any character sequence into valid tokens. However, this comes at a cost. Tokenizers are overly sensitive to variation in casing, diacritization, and other, let's say, low-level variations of the characters. At the table below, you can see a check phrase that is being coarsely split when the phrase is written according to the rules, while it overly splits when it is fully uppercased or de-diacritized. The easiest solution is, of course, to strip off the text of all diacritics and all casings, and this is done in some big modules such as Burton Cased. But we will lose some information about the expressivity or the formality of the texts, especially if we talk about the online data. There have been several solutions that aimed at keeping information about casing while maintaining the subword stability. One of them is called inline approach, which is done through lowercasing every word, but reallocating the information about casing into a prepending special token, which we call flag. Here you can see that different casings of the word hello are split into lowercase words hello and prepended with the tags where T stands for title cased, U for uppercased, and so on. And as a result, you can see that the word will be tokenized uniformly, no matter how it is cased. Such an approach, compared to others like factorization or data augmentation, is more interpretable. However, the existing solutions seem to be suboptimal in terms of encoded sequence lengths, and we also do not know of the experiments with such an approach towards diacritization handling. Therefore, in this work, we present two systems. First is yet another inline casing algorithm, which we call InCa. Its main advantage is that it is frequency-based and it assigns the flags only to the non-frequent casings. This allows to minimize the encoded token lengths. And also, it makes it robust to different types of noising. Secondly, we present the first, to our knowledge, inline diacritization algorithm, which is called InDia, that also makes system more robust to various types of de-diacritization noise. And finally, we make a proof of concept on the empty task on the Czech-Ukrainian language pair. So let's look at the principle of work of InCa. It is applied in three steps: the training, encoding, and decoding. So at the training step, we take a corpus and collect the counts of any possible casing for any unique uncased character sequence. Such character sequences we call bases. Then we choose the most frequent casing for each base and store this most frequent casing in the dictionary. For the sake of shortness, we only memorize the non-lowercase casings if they are the most frequent ones. And now that the dictionary is ready, we can apply it at the encoding stage. So consider the sentence: John Baker sold an iPhone 32 gigabytes and an HTC 64 gigabytes. You can see some title-cased words, some upper-cased ones, some even with the inline title casing like iPhone. And now let's see how our algorithm would cope with that. The distinctive feature of our inline approach is that given the dictionary that we created at the previous step, we mark only the non-frequent or out-of-dictionary casings. So, for example, we start with the word John. It is title cased, but it is in the dictionary as well. So we mark, since it is in the dictionary, we just lowercase it without losing any information because it is the most frequent casing. The next word, baker, is not in the dictionary and is not lowercased, and therefore we prepend it with an explicit title cased flag. Third word, sold, is not in the dictionary, but it is lowercase, so we leave it as is. Then again, iPhone, we lowercase and do it without any flags since we store such a casing in the dictionary. Now again, with the gigabyte abbreviation, we store it without a flag since such a casing, the fully uppercase casing, is in the dictionary. HTC is not in the dictionary again, so we lowercase it and prepend it with an explicit flag. And gigabyte is in the dictionary, but with a different casing. Therefore, we explicitly encode it with a flag that shows that it should be lowercased. And as a result, although sentence consists of 5 cased words, we only put flags in front of 3 of them. We can also look at the classical inline casing approaches and compare it to ours. So in classical inline casing, every cased word should be prepended. Also, words like iPhone would tend to be over-segmented because the explicit information would be put before each casing occurrence. While in our case, it is unnecessary because we just memorize the most frequent casing. Therefore, we get shorter token sequences. We also get consistent encoding of words under different casing. For example, we have seen the 2 gigabyte abbreviations, and in both cases that they would be stored as the same base, but sometimes they would be just explicitly prepended. We also introduced the flags on the sentence level to shorten the sequences, the encoded sequences even more. For example, below you can see the all caps sentence, fully uppercased, and a single flag that says that the whole next sentence should be uppercased. Importantly, our system is also fully reversible given the dictionary that we trained at the training step. Now, if we talk about inline diacritization, the core principle of InDia is quite similar to that of inline casing by us. So at the training step, we count all possible diacritizations for each unique latent character base, and we store the most frequent diacritizations for each base. And then at the encoding step, we again de-diacritize each word, but only put flags where the diacritization is not the most frequent one, or is outside of the dictionary. For instance, with the base zebra, the most frequent diacritization would include the sign called check on the first character, on the character je. If we need to encode the sequence below, for the first word, we would have to put a flag that would explicitly say that the first character should not be diacritized compared to the most frequent diacritization. Analogously, at the second word, there is one more flag compared to one more diacritization compared to the most frequent one. And again, we would have to put a flag saying that the fifth character should be assigned with the diacritization called charka. The significant difference from the inline approach to casing is that the flags related to diacritizations will be longer than in casing because we need to deterministically show the information about which particular character has to be diacritized and how. For instance, with an example of the word below, where there are 2 diacritized symbols and the word itself is not in the dictionary, it would take us at least 4 characters to show to store the information about the character indices and the diacritics. Now we can test our systems on the downstream task, which is Ukrainian to Czech machine translation. The experimental settings are quite tiny. We have around 8 million training sentences. We use base transformer implementation by Marian, and we train the system for 16 epochs. We are also interested in both extrinsic and intrinsic evaluation. So for extrinsic one, we are using the standard metrics like blur, character F, and comet. And for intrinsic ones, we measure the number of characters per token, which shows the optimality in terms of the granularity of tokenization of the encoded token length. And we apply it both to the encoded texts and to the inner unique tokenizer vocabulary items, subword tokenizer vocabulary items. Another metric that we use is the average rank, which shows how uniformly the frequencies of unique tokens are in the encoded text. Firstly, we compared our inline casing to the other existing inline casing systems. Specifically, we compared it to the baseline with no inline method. We compare two variants of our system, with and without a dictionary, and also two solutions which exist in production, which is Marian system, which is also frequency based, but it stores the information about frequencies differently from ours. And Token Monster. This is a simultaneous inline preprocessor and tokenizer, whose main point is allowing for multi-word tokens. We compared the translation quality for both the regular test sets with no noise and different types of case noising, namely fully uppercase text, fully lowercase text, and 10% randomly cased words. The results were the following. For both directions and for most types of noise, the performance of all systems was almost the same, as you can see on the left part of the graph. The only difference was the fully uppercase noise, where our sentence level flags helped to reach the non-noise performance. You can see it on in the green bar on the right part of the graph, and you can see that it is nearly as under non-noised conditions. Now, if we turn to the intrinsic evaluation, we see even more interesting details. First, we see that our system is more stable in terms of the intrinsic behavior. For example, the average rank spread for other systems is over 200 ranks usually, while our system makes the spread less than 100 ranks. And secondly, if we look at the tokenizer dictionary entries, we see that our tokens become half a character longer on average. And what is even more important, in our systems, in the other systems, many tokens in the dictionaries have their duplicates that differ only in casing. While our systems allow to get rid of such doublets and allocate the capacities to the new unique character sequences. The second experiment was dedicated to inline diacritization. Since we don't know of other solutions of that kind, we only compared it to baseline and to two of our modifications of the InDia approach. The first modification allows to put a single character flag to each word, and another is the dictionary-less naive implementation of that. The results, and yes, we tested the general translation task as well as translation of the fully or partially de-diacritized texts. The results were quite promising. For the non-noise data, we got the comparable performance to the of all the systems. But for the de-diacritized data, our systems are showing up to double increase compared to the baseline system. So I hope that the overview was quite demonstrative, yet we have several other interesting observations. For example, we claim that our systems are more interpretable than the data augmentation approach, and that the intrinsic metric of Renyi efficiency that is now being popular as the intrinsic evaluation of the tokenizer quality. So this Renyi efficiency might be problematic for the inline casing evaluation. For all of that, please check out our paper and source code that you can see on the QR, and thank you very much for your attention.